So this idea about sandwich planet formation, in a nutshell, the punchline is that we're trying to form a little planet here in between two more massive planets. So this is the little planet that I'm referring to here. This was actually a really nice piece of work done by an undergraduate student, actually. He was my master's student. He stayed on and did a summer project with me. And by the end of the summer project, he actually had a very nice paper draft. This then got delayed a little bit because I went off on maternity leave. But then we submitted it last year and it was accepted. What I'll do no, it didn't like that. There we go. What I'll start by doing is to give you quite an extensive introduction. I'm very aware that people come from different backgrounds and got little different exposure to planets and planet formation, which is the area that I work on. So I'll give you a bit of quite an extensive introduction on sort of the theory and the observations that we just need to sort of set the scene for what I'm then going to tell you in the second part of this talk, which is about this concept of sandwich planet formation. So to start off at the very beginning, just to sort of set the scene a little bit, what you're seeing here is a simulation of a molecular cloud. It's rotating, it's collapsing. What you're seeing is a star forming environment. So all these little dots that you see are stars that are forming. And what you also see is around those stars that form, you actually get disks forming as well in some of these cases, right? So here's one example here in the bottom right corner where you've got this disk of gas and dust that's formed around the same material that the stars are formed out of. And it's in these disks of gas and dust that planets form. So these are disks that we call protoplanetary disks. Now, if I just sort of show you sort of some schematic diagrams of essentially what I just showed you, but I'll sort of walk you through it. What happens in the very, very early stages is that you have this upper left cartoon here, where you've got the star developing in the middle. You've got a little bit of a disk sort of starting to form around it. Essentially, that material is sort of starting to form that disk, and it's flowing inwards. You've also got a little bit of outflows as well. If we then look at the top right-hand side over time, what has happened is that star and disk system sort of built up. It's still surrounded in the envelopes, so material is still accreting onto that disk. And you've also got outflows as well. But then as time progresses, we then end up in the bottom left corner where we actually have a star and a disk system. There's no more envelope. And then in this system, planets can actually form. And in fact, planets, the starting point of planet formation can actually be really, really early on. But we see more of the planet formation happening as the disk continues to evolve. And then eventually that disk will either dissipate. There may be winds that come off from the star, and these disk winds will actually get rid of some of the material from the disk. Some of that material will actually accrete onto the star, will accrete onto the planets. There may be flybys that get rid of the disk material. There's quite a few ways in which you can actually lose that disk material. But the end result is that you get your planetary system around your star. So this is actually an artist's impression of a planet-forming disk. It's what we call a protoplanetary disk. And these disks are made of gas and dust. And it's very important to see the dynamics of both the gas and the dust. And I'll talk about that as we go along. But let's actually look at how planets actually form. So there are a couple of ways in which planets form, and the way that I'm going to talk about here is what we call the core accretion method. So this is where the dust component in the disk will actually come together. So the dust will actually collide with each other. It will probably, they'll like stick or they'll break apart, if the collisions are very violent. But the idea with planet formation is that the dust will stick together. It will eventually grow. More and more dust will stick to it. Eventually, that's what you have in step 1. And then eventually in step 2, you have this core that has built up. It's sufficiently massive that it can then start to gravitationally attract dust and gas to it. Okay, in step 1, we're not gravitationally attracting the dust. It's just in step 2 where that core is big enough that the gas and dust can really be pulled more and more onto that core. And then if time allows, if there's enough disk material left, and that core gets sufficiently massive, you end up in step 3, in this third stage, which we call runaway gas accretion. And that planetary core is really massive, that it really pulls a lot of gas onto it, and you would end up with a gas giant planet. So that sort of sets a scene for how planets can actually form in disks. Now, from a planet formation theory perspective, there are a couple of reasons why we expect planets to be more and more massive further out in a disk. The first is this concept of what we call the pebble isolation mass. So let me explain this. Here is a schematic diagram of my star and the disk. And you actually have these grey dots in the, well, let me start here. It's this sort of light blue dot here in the middle is the planetary core. These grey dots are basically meant to represent dust in the disk. This is as good as my artistic abilities gets. So what's, in fact, these grey dots should actually be over the whole disk, not just in the outer part, but what I'm going to, for the purposes of what I'm going to illustrate here, I just want you to focus on the dust in the outer part of the disk. Now, if that planetary core is really small, that dust from the outer part of the disk here can actually flow with the disk material. It can flow past the planet and into the inner part of the disk. But if this planetary core is big enough, this dust will actually flow towards the planet, and it will actually stop in a part of the disk just exterior to that planet's location. And what the planet has done in this particular case is that it has actually perturbed the disk, the gas disk profile, which has then caused the dust to actually collect there and stop. And I'll talk in a little bit more detail as we go on about exactly the physics of exactly what goes on here. So I will come back to this point. But essentially, that planet mass, that minimum mass that you have for this planet, where you actually get the pebbles, which is what we call these dust particles, where you get these collecting in this region just exterior to the planet, that planet mass is what we call the pebble isolation mass. Now, the pebble isolation mass actually scales with the aspect ratio of the disk. So let me just take one step back. Let me tell you what the aspect ratio is at any one particular location in the disk. You've got the height of the disk divided by the radial location that you're interested in. That is the aspect ratio. This aspect ratio actually typically increases with radius. So it's actually these disks that are flared. You actually, when you work through the maths and when you look at typical disks, actually those what you find is that H over R is proportional to R to some positive number, which means that this isolation mass increases with radius. And if the isolation mass increases with radius, that planetary core that you have over here can be larger and larger further out in the disk. And if you've got a larger and larger planetary core further out in the disk, then that end planet that you would expect might be larger and larger further out. Let me also just correct myself a little bit. I say larger. I don't mean size, actually. I should have said more massive. So I might use larger and smaller interchangeably with more massive and less massive, but I'm really thinking about the mass of the planet here. Okay. Okay. Yes. So this is just simply that red text is just simply is just saying what I've just said. So there's the second concept that we can think about with regards to the size of the mass of the planet with distance from the central star is this concept called the Hill radius. So the Hill radius is essentially the radius around the planet where the planet has this gravitational influence, right? And so it can accrete material from around it within that region very easily. And the Hill radius is given by the distance from the central star and also the planet to star mass ratio to the 1 cubed. Now, when we actually, so what you can see here is that the Hill radius increases as you go further out in the disk. And when you actually look at how much disk material is available to a planetary core further out in the disk. So let's suppose you have the same mass planet in the inner disk and the outer disk, just simply because of this term A, that Hill radius would be larger. You'd have a larger gravitational influence further out in the disk. But the surface mass density in the outer part of the disk actually also decreases. So the interesting aspect to actually look at is this quantity called the local disk mass, right? So if I was a planet in the inner part of the disk versus same mass planet in the outer part of the disk, how much mass is available to it to grow in its Hill sphere. And when you actually do the calculations, the local disk mass is the surface mass density times by r squared. In the previous slide I used A. Apologies, this is the distance. R is the distance to the distance in the disk that you're thinking about. And for typical protoplanetary disks, sigma drops as typically r to the minus a half to r to the minus 1.5, typically. You don't have the surface mass density dropping steeper than r to the minus 2. So the point here is that the disk mass actually increases with radius because of that r squared term. So as a result of that local disk mass increasing, you'd expect again to have a larger a more massive planet further out in the disk. Okay, so here I've just talked to you about the fact that we should expect more and more massive planets as we go out in the disk. Mother Nature is not so kind to us and does not follow this trend necessarily. So it is very different in reality. This is a plot of a subset of planets that we were actually looking at in a paper back in 2019. And what we have here is the orbital period of observed planets, so effectively distance away from the central star. And these are the planet masses. Now, if there are planets in the same planetary system, they're actually connected by a peak line. Right, so for example, if we look at this one and this one, this actually follows the trend, right? The further out you go in the planetary system, the more massive the planet, right? However, there are also situations where that trend isn't followed. Here's one example, right? We have a lower mass planet further out compared to in the inner part of the disk. And then you've got planets with planetary systems with multiple planets, and you just see that it's sort of zigzagging all over the place, right? So it's not following that really nice, theoretically motivated trend. Okay, let's actually look at some of the, so those are the exoplanet observations. Let's actually look at protoplanetary disk observations. So these are observations that have come from ALMA in the last few years, absolutely spectacular observations of disks, which are showing some really, really nice, interesting structures. You've got, predominantly, you've got rings and gaps, like you can see in this image here. These are your gaps, these are your rings. There are also some asymmetries here. There are also some spiral structures, if you look carefully. And all of these structures in protoplanetary disks are telling us about planet formation and planet evolutionary processes that are happening in disks. Now, if we just look at this one, since it's a bigger image here, what we suspect with some of these with some of these images. Sorry, for those that are online, I'm just going to point to this image on the right-hand side. What we see is that these gaps are potentially, we don't know for definite, but potentially formed by planets. And what we expect when we have planets in disks is that they will carve out a gap, and that is exactly what you're seeing here, right? And what we'll also see, and I'll show you in just a minute, is that we actually get rings forming as a result of planets being embedded in the disk. Now, if we have rings forming in the disk, this is a nice, very, very definite ring here, the red one. One question that we can ask is, well, what is actually happening in those rings, right? They're collecting dust, they're collecting gas. Is there more planet formation happening in these rings? And that's the question that we're trying to address. So let me talk you through a little bit more of the physics of what goes on when you've actually got a planet in a disk. Now, if what you're seeing, if we just look at the schematic diagram on the left-hand side, this is a plot against pressure against radius, right? So it's the azimuth and the average pressure in the disk against distance from the central star. Now, if there was no planet in the disk, what you would see is that this pressure would just simply drop off with radius, right? What happens as a result of this, as a result of the planet being in the disk, is that you actually have this region where the pressure profile actually drops, and then it increases again just here where you have a pressure maximum. And that pressure maximum is actually really key for dust collection. So let's actually think about what happens to the dust in this disk in the presence of the planet. So in the outer part of the disk, where you've got this little dust particle that I've drawn, what happens is that this dust particle is orbiting around the central star, and it's orbiting at a Keplerian velocity. The gas is also orbiting, and the equation of motion for the gas is what you see in this upper right? The first term on the right-hand side is the Keplerian motion here. This is the gravity term. And the second term is the pressure term. So the gas feels the pressure in the disk, and that actually affects its azimuthal motion in the disk. Now, in the outer part of this disk, where this pressure gradient is negative, you essentially have a negative term here, which actually means that the gas is orbiting at a sub-Keplerian velocity, but the dust doesn't feel the pressure term, it's simply orbiting at a Keplerian velocity, right? So the end result is that the dust actually feels a little bit of a headwind because it's moving faster than the gas. And as a result of that headwind that it feels, it actually loses angular momentum. The dust ends up moving inwards. That's what you see with this blue arrow. And as a result, it starts to move in the inwards direction. Now, the exact opposite occurs when you have dust, when you have positive pressure gradients, right? That dp by dr term in the equation here is positive, so that gas is traveling at a super Keplerian velocity, but the dust is traveling at is orbiting around at a at a Keplerian velocity. So it actually feels now a tailwind instead of a headwind. And as a result, that dust particle actually gains angular momentum and moves outwards. So what's the end result, right? You have particles that are traveling inwards from the outer part of the disk, and from this part of the disk where the pressure gradient is positive, you have particles moving outwards. And the end result is that they actually collect here at the pressure maximum. And now this is a 1D profile, if we now think about the entire 2D profile of the disk, you end up getting a ring of particles that have collected at that pressure maximum. And this is one example of a simulation by Giovanni Rizzotti, where he was actually looking at planets in disks and just looking at the interaction between the gas and the dust. And what he sees here, this dark red ring, is illustrating the surface, the dust surface mass density in the disk. So we know that when you have a planet in the disk, and when it can create a pressure maximum, you can actually get a ring of dust. You can actually, but that's sort of, you know, if the planet's mass is a little bit lower, so that it doesn't perturb the pressure profile too much, you don't get this pressure maximum that I was where you see all these particles collecting. You actually get a point of inflection. But the physics behind the motion of the dust is actually the same, right? With that negative pressure gradient, dust is still moving inwards. It's moving here. It's negative here in the middle where you've got that point of inflection. It's still moving inwards, and then it's in the inner part of the disk. It continues to move inwards. But what we have here is that because this pressure gradient is particularly steep, you actually have the drift velocity of the dust, which depends on the pressure gradient, being quite large. And I've sort of tried to represent this with the size of the arrows. Whereas when you sort of hit this sort of point of inflection, you actually get a pressure gradient which is less steep. So the dust travels a little bit slower, and then as it moves into the inner part of the disk, again, you've got a steep pressure gradient, so it continues to move in fast. So Giovanni Rizzotti actually coined this term a traffic jam. I think this describes it very nicely. Just imagine you're in a traffic jam. You're continuing to move in the same direction. It's just that cars are piling up, and then eventually you kind of leave that traffic jam and you continue moving on. And that's sort of what he's saying here, is that this dust that's piling up here is somewhat of a traffic jam. So so now so that's sort of all the background that we need to know in order to understand this concept of sandwich planet formation. So I'm now going to take you through what we were actually doing. Okay, so here we have 4 schematic diagrams of pressure profiles in 4 different simulations that we were looking at. And what we were essentially doing is to show, so this is something that's already known. This is not the new bit, but what we were doing was to look at what does the pressure profile look like when you've got 2 small, again, this is where I'm going to use it, where I'm going to clarify by small, I mean low mass, 2 low mass planets. We have 2 sort of points of inflections. You've got a massive planet where you end up getting a pressure maximum just here on the right hand side, and then you've got a low mass planet where you've got a point of inflection. Then if we look at the bottom left, what we're doing is to essentially reverse that, and we have a small inner planet and a big outer planet, where you've got a point of inflection here in the inner part and a pressure maximum in the outer part. And then in the final case, you've got 2 massive planets where both of them create pressure maxima. And the question we were asking is, well, okay, if you've got two planets present instead of one, what happens to that dust motion from the outer part of the disk into the inner part of the disk? So I'm now going to take you through each of these four scenarios, and we can look at the results sort of step by step. It's a little bit, those of you in the room, it's just at the bottom. I'll just explain what this is. On the left-hand side, you're seeing the schematic diagram from the slide before. This is the case where you've got two low mass planets, and then on the right-hand side, you've got the dust surface mass density against radius. This is all in code units. We do in the paper, we do actually put it into perspective with some some actual physical numbers, and I'll actually talk through some of those as we think about some of the observations. But if we go with the code units to start off with, the black dashed line that you see is the initial surface mass density of the dust in the disk. The two vertical dotted grey lines are the locations of the planets. So we've got them at r=1 and r=2. The red line shows you the simulation, the equivalent simulation where we don't have the planet at r=2, we only have the planet at r=1, so that we can compare the situation with two planets compared to when you've only got a single planet at r=1. Now, what we're particularly interested in is what happens to this, the dust collection here in between the two planets. Now, when you've got a second planet there, what you can see is that that second planet, we look at the blue line, it's created a little bit of a dust trap here. It's a traffic jam, essentially. Dust is collected here, it's continuing to move inwards, but it's continuing to supply the inner part of the disk. And you actually see that the dust collection that you have here in the in between the two planets doesn't change when you introduce that second planet. So not a lot of difference between the two cases here. Let's look at the case where you've got a more massive inner planet and a low mass outer planet. And again, what you see between the red and the blue line, in fact, they're virtually on top of each other here. There's not much difference in what you find here. And the reason is that that low mass planet doesn't really do much to stop the dust supply. The dust can still come past that low mass planet from the outer part of the disk and still end up in this region in between the two planets. So again, not too much of a difference there. Things start becoming more different when you actually reverse it. So you've got the more massive outer planet and the low mass inner planet. What happens as a result of, if we look at the schematic diagram on the left-hand side, exterior to this massive planet, you've actually got this pressure trap. This is that pressure maximum where dust traps, right? And if we look over at the right-hand side, what we're seeing is this collection here in the blue line. That pressure trap is leading to all the dust that's coming inwards, just collecting in that pressure maximum, and it can't escape that pressure maximum because it just stays there. That's the that was the dust ring that I had showed you before. And what happens in the inner part of the disk is that you actually see that all this material that was here before is just simply drained onto the central star. And that's why the dust surface mass density in the inner part of the disk is much lower than in the case when you have the red, when you've just got a single planet. There's just no way that dust can be resupplied to that inner disk. And then the final case is the one where we've got two massive planets. So here is where you have two pressure maxima on the left-hand side. Here's the outer one, and here's the inner pressure maxima. And if we look at what's happening on the right-hand side, there's something interesting here. So just as we saw on the previous slide, as a result of that outer planet being a massive one which can trap dust, you actually get a dust trap here. But what's interesting is what happens here. So as a result of that outer pressure maximum, the dust comes from the outer part of the disk, it collects here. There's no way it can then continue to move into the inner part of the disk. So what we have left here is a reduced amount of dust compared to the case of the single planet, right? In the red case, material will be continued to supply to it, and you will just get more and more material trapped in that pressure maximum. But that's just not possible in the case with two planets because you've restricted the supply. So now we can start thinking about, well, what would actually happen if we were to have this kind of scenario where you've ended up with two planets, one at r equals 1, one at r equals 2, what would actually happen to that dust that's collected in between the two? If that dust was to eventually come together and it would grow, it's a very good environment for growth to happen because the collisions in that environment are not very strong. They're not very violent because the dust is just sort of orbiting very, very nicely and calmly. In principle, you could expect a planet to grow in that dust trap. But because we've got a reduced amount of dust that we've collected there, that planet that we might form would actually be a low mass planet compared to those outer two planets. So if I just illustrate, again, this is as good as my artistic abilities get, that conventional, what I call the conventional planet formation scenario that I described according to theory, is that we should expect planets to be sort of more and more massive further out in the planetary system. Here we've got the Earth, we've got super Earth, which is sort of about 10 Earth masses, and then I've illustrated this with Neptune, which is sort of 17 Earth masses. And if I compare that to the planet formation scenario that we're presenting here, is that if you've got two more massive planets that are represented with Neptune in the inner and outer part, and if you do have dust collecting in the inner part, which can then go on to form planets, we would expect that planet that would form would actually be low in mass. So it would be the architecture of the planetary system would be really different compared to what we might expect from theory. So then we can ask the question, well, okay, is that actually the case when we look at observations of planets? So now we're looking at we looked at the NASA Exoplanet Archive. We basically looked at any planetary systems that had 3 or more planets. We wanted to be quite, we wanted to make sure that we had good mass measurements. Not all planets have got good mass measurements or have mass measurements at all, because quite often we're measuring the radii of the planets and not the masses. And what we wanted to know is that even when you consider the error bars on those mass measurements, are there any planets that are what we would term sandwiched planets? We got about, I think it was 17 planetary systems in the end, once we'd sort of made this cut, and then we said, right, okay, which of those are actually sandwiched? And there are about six of them. So here, the blue planet is what we call the sandwiched planet. The planet either side of the blue planet are the planets that are sandwiching it, and the size of these planets, as well as the color, illustrates its mass. And then the gray planets are simply other planets in that planetary system. So we're talking about small number statistics, and I cannot say that, oh yes, absolutely, there are, sandwich planet formation is a very is something that's happening a lot, but certainly we've got some suggestions of sandwich planetary systems, enough to make it interesting enough to sort of explore further. So we kind of, when we looked at the observations, we actually kind of took, we sort of relaxed some of the precision side of things, just to sort of see how this would change. And we were still seeing that, yes, there's still a reasonable proportion of planetary systems to make it sufficiently interesting. We also, as an A side, looked at systems which had 2 or more planets, where we didn't necessarily detect the sandwich planet side of things, but we could see that the outer planet was lower in mass than the one just interior to it. And then we sort of put that question out, well, actually, if there is a currently unobserved planet in the outer part, and if that planet was more massive than the outer one, then again, there's a bunch of planetary systems that could potentially be sandwiched planets, but that's for the observers to sort of go out and try and think about that in a little bit more detail. So that takes me to the end of my talk. So I'll just very quickly summarize what I talked to you about. So what we were doing was to look at, when you've got 2 planets in a planetary system, in a protoplanetary disk, what impact does that have on the dust flow and the collection of dust in between those 2 planets, compared to if you only had 1 planet. And what we found was that when you had a low mass outer planet, that really didn't do much it didn't change anything compared to the single planet case. When you've got a more massive outer planet, that really does change things. And especially when you've got 2 massive planets, we actually find that dust collection in between those 2 planets is reduced. And those are the situations where you might potentially get sandwiched planets that could potentially form. And then finally, I showed you that we certainly see evidence of planetary systems that have this sandwich planet architecture. It remains to be seen whether or not those actually formed via this mechanism, or whether it was something else, but certainly one to explore further. So that takes me to the very end. I'm just going to very quickly spend about half a minute just telling you about something that I think that people in this group might be interested in. We're actually just at the point where we at Warwick are starting to think about kind of building a community of people that work on various different kinds of astrophysical disks. One way, there's a couple of ways in which we're doing this. One way is to develop, to have an email list where people can sort of advertise disk-related jobs, meetings, conferences, etc., PhD positions. This is a very long, convoluted. I really should get a shortened version of that, but I will. But you have these slides, so you can certainly get to that link. So if you're interested, I do encourage you to sign up and post anything send anything out that's relevant. And then the second aspect is that we're hoping to have a kickoff meeting in September 2024, where we'll just bring the various members of the astrophysical disk community together to kind of, think about sort of cross collaboration, thinking about kind of, just understanding what's happening in different disk communities. And that's really, both of these are with a goal to just kind of build this sort of UK and Ireland community of people working on astrophysical disks. So with that, I will go back to my summary, and happy to take any questions.
Thank you very much, Professor. Thank you. Any questions from the audience here or on Zoom? Alan?
Hi, that was great, thanks. I was wondering for the sort of sandwich kind of disk as it's sort of building up before it's worrying if forming planets or not. Is there a point where you can have enough mass in it that it becomes unstable and then come back to the end?
Yes, in the very, very, very early stages. So if I go back to my schematic diagram here, there is definitely a phase here where the disk will be self-gravitating. That's another part of my research interest that I haven't actually talked about today. And indeed, in this, especially when it's when the mass is being built up in that upper right image, you can have the disk being 10% of the star mass or even higher. And when it's that high, that disk is gravitationally unstable, and that disk can fragment. And that is sort of the second way in which you might form planets. So those fragments would be sort of giant gas balls that would form. You might then ultimately sort of sediment dust into the inner parts to actually form the core, and you typically form massive planets very quickly in that case. Or brown dwarfs, you can actually get to quite large masses. Thank you.
Any other questions? I have a problem, so we're getting pretty quiet. I wanted to ask, if I understood the formation mechanism described correctly, you should expect that smaller sandwich always be quite close to the pressure profile. Yeah, I didn't see that very clearly in the example system.
Yeah, it's a very, very good point. Now, I guess I would probably, okay, so let me just let's go back to the there we go. I think it's oh no, it's actually even here. There we go. So you're referring to this part on the right hand side where you actually see that peak being really, really close here. Okay. Right, there's lots of things at play here. Okay, firstly, it depends on the mass of the planet here. The more massive the planet is, the more it will push that pressure peak further out. And so in this particular simulation, we had 20 Earth mass planets here and 35 Earth mass planets here. If you change that a little bit and that 20 was actually something larger, you probably actually push that further out. Then the other aspect that you don't see in or that's not easy to tell here is what's the evolution of those planets that has taken place. So when we're simulating these disks, we're talking about the first few million years, right? And then these are much, much older, right? And so a whole load of evolution has happened in between. If we come back to this diagram here, if we look at the bottom left, between the planets actually forming, they will migrate in the disk. They could potentially scatter, especially when you sort of loss in the disk material and they interact with each other, they can scatter more easily. So there's quite a bit of evolution that can actually take place, and so
it's messy, isn't it?
It's messy, and we wouldn't be able to kind of say yes, it absolutely definitely should be really close to the planet or not, because it depends on so much.
And leads to my second question, which was, we assume also that central sandwich planet should also have formed, it has to have formed after the bigger planets.
Yeah.
Is there any way of, not the planet expert, any way of measuring the formation time and being able to see differences there, or are the differences too small to be measured?
Yeah, there. Okay, it would be. I think it probably would be a little bit too small to be measurable, because although it would form later, in the grand scheme of things, we're actually still looking at planets that are sort of, in this case, we're talking about disk lifetime is sort of up to 10 million years. Whereas when we're observing planets it's way after that. We're talking about billions of years, and so it's
There's no funky radioactive isotopes. I
that's,
mean, you can't measure them anywhere near distances.
so we would probably just one thing that I'm not sure about is what goes on in the chemistry in disks. I suspect there could be something really interesting that could happen, because a lot of the chemical reactions essentially depend on the pressure and the temperature in the different locations in the disk. And I'm wondering whether there could be some kind of chemical signature that could then indicate, well, a couple of things. One, the location of the planets and whether or not you can actually sort of the location of the formation location of the planets, but then also whether or not it could give some indication of the time, as you know, which ones formed first and which ones didn't. That would be great to know, because if we could say, oh yes, these two definitely formed first and then this one in the middle formed afterwards, then there's a very, very nice way of kind of being able to link this formation mechanism to the observations. I'll have to talk to some of my astrochemistry friends and see if they can come up with something that you know, some way of finding an observational signature, I suppose, for this. That would be nice.
One more question. Thanks.
Can I ask a related sort of trying to get you to be more specific? You gave in terms of all the period, you actually showed a very small order of periods. Is that where you think this mechanism would be most at play?
Not necessarily, because in principle, if we come back to
Your plot showed kind of less than 50 days.
that's right, they were indeed. Now the reason why I say not necessarily is that you could actually the mass of the planet that you need to reach the pebble isolation mass varies with disk location. But it also varies with disk viscosity as well. So if you lower the disk viscosity, actually you don't need as massive planets. So I in the big simulation, I said that we used a 20 and a 35 Earth mass planet. These were for a simulation where the disk viscosity, where the alpha, the Shikura-Tsarnaev alpha was 10 to the -3. When we did these simulations with 10 to the -4, I think we were looking at 9, the big simulation was 9 and 18. So you didn't need as massive planets. And from a similar perspective, if we actually moved inwards, because the pebble isolation mass depends on the aspect ratio. Let's come back to here we go. The aspect ratio is actually lower in the inner parts of the disk compared to the outer part, and so you would end up with smaller mass planets that are needed to reach to get you that pressure bump. So I think so with this plot here, I was simply illustrating it because I liked the way we could kind of see the zigzags and the ups and the downs. But in principle, I think this could be anywhere. It's not, there's no reason to believe it should happen in one location of the disk preferentially. There is a reason actually, in one particular case actually, if we think about the planet formation timescales. So the formation timescales are actually longer further out in the disk. So the likelihood of getting those 2 planets forming, followed by a 3rd planet forming, having enough time to do all of that in the outer parts of the disk is lower. So from that perspective, maybe actually what you said, that's a really interesting spot, that actually maybe it is easier for this to happen in the inner parts of the disk. Yeah.
Right. let's thank our speaker again.
Thank you.